So a reminder, so the next up, we have 2 lightning talks. And if you didn't see the procedure of how this works, there's a QR code here, which takes you to an application where you can vote. Because we have a lightning talk competition going. So you'll be able to, right now it's not open, but it will be open when the students are speaking. And you'll be able to vote, the maximum is 7, right? On a scale of 1 to 7. So please please grab the code now while it's up. And it will be up again after the first talk. Okay, so our lightning talks now are from students Shreya Sharma and Anna Wadwa. And I'd like to call our first speaker here. Shreya? Yeah. Thank you. And change the slides with the green arrow.
With the green arrow? Okay, thank you. Good afternoon, everyone. I am Shreya Sharma, and today I'll present on how we can use satellite observations to model impacts on the ground. I want to bring your attention to one of the biggest challenges the Earth is facing today. This is India Gate in New Delhi on a clear day. However, on most days, it looks something like this. Now, this is due to very widespread air pollution occurring in several places in the world. If you have the Apple Weather app, you can look at the air quality at any location to see how widespread this problem is, and also get details about what the composition of air is in different locations, including things like ozone, particulate matter, or PM 2.5, and things like oxides of nitrogen, sulfur, and carbon. Inhaling some of these have shown to cause very serious health problems. Ozone, while very helpful at altitude in terms of blocking the UV rays, can inflame the alveoli of your lung when you inhale it, causing asthma and bronchitis. Similarly, PM 2.5 is small enough to enter into your bloodstream, causing things like certain cancers and other diseases. It is estimated that air pollution kills 1 in 8 people globally, and more than 90% of these deaths occur in low and middle income countries. While it's very unlikely that we can control the growth of different industries, we can take certain decisions to reduce their impacts. To evaluate the effects of different decisions, running experiments for every policy we want to run is not really feasible. So we instead use chemical transport models. You can think of this as essentially a model of the Earth's atmosphere divided into several grid cells. In each grid cell, we have boundary conditions. These could be things like whether there is land or water there, some initial conditions like what the chemical composition of the air is in each of the grid cell, and how they are transported around the globe through different wind patterns, which means it doesn't just become a local issue, but a global issue. Why these models are so useful is that they can help quantify the contribution of different sources or mechanisms to observed environmental outcomes. Now, what I mean by this is that if I have some baseline conditions B, and I have some emissions E, if I run 2 simulations with and without these emissions, I can very easily quantify what the effect of emission E is in terms of any observed change that I see. Now, all this is great, but how do we know if our results can actually be trusted? For this, we use data from Earth observation satellites to validate our simulations. One such satellite used specifically for air quality is by using the Ozone Monitoring Instrument, or OMI, aboard the Aura satellite, and this provides very detailed measurements. Geoschem is one chemical transport model, which I use very frequently in my research, and it is open source. And this is a comparison of how Geoschem is able to capture the ozone representation very well. Every time a new version of the model is released, we try to first validate it with the latest data that we get from the Earth observations so that it can be as good as the data that we get. This is very critical to ensure that our models are free from any biases in terms of the latitude or seasonal variations, and we can really simulate what we want to get. So let us see one use case in action. I work on sustainable aviation, and I simulated the emissions of all of the jet fuel burnt by all aircraft in a certain year. This is what the emissions look like, and we can clearly see patterns of where aircraft are flying, where these emissions are occurring, and how these different continents are interconnected. So similarly, I ran 2 cases, and I got the results for, I subtracted them to get the results for the aviation attributable change. Here are the results. For a change in ozone, we see that most of these effects are felt in the northern hemisphere, and this is very pronounced in the mountainous regions of Central Asia and Western US. For change in PM, or particulate matter 2.5, there are very large hotspots in densely populated regions of India and China, followed by places in Europe. Now, the thing to note here is that the spatial distribution of ozone and PM 2.5 is very different from the spatial distribution of where the emissions occurred, as on top. And this could only be assessed through the use of these chemical transport models, which in turn really rely on data from Earth observation satellites for its accuracy. So it's very important that we continue working on increasing both the temporal and spatial resolution of these observations, so we can have a better knowledge on who's being affected by our activities, and also more accurately simulate whether a change in our action is actually leading to the desired effect on our people. I want to conclude with a quote from Carl Sagan. Space technology today has enabled us to venture to the moon and beyond, and so it's our duty to ensure that we do not destroy our beloved planet Earth. Thank you.
Thank you, and please, voting is now open for Shreya, and the QR code is on the screen. So our next lightning talk speaker, I apologize, I misspoke earlier, is PhD candidate Amelia Gagnon, and I would like to welcome Amelia now. Thank you.
Hey all, good afternoon, engineers, scientists, educators, and space friends. I'm here to talk to you about examining mental workload with light, and specifically functional near-infrared spectroscopy. All right, so humans in space. Over 700 individuals have gone to space, but if you take that look at the actual launches, that can be extended up to over 1,500 people have been launched in space, including repeat visitors. This is tied to a rise in space tourism, as we've seen in the news, especially last weekend. Long-duration mission plans, reaching new distances such as the moon and Mars, and humans are going to be very dependent on the tools that we give them, especially with delays in communication and delays in returning back to Earth again. So the space environment is hard on machines. I'm sure every person has brought up in this particular venue how hard space is. Space is also incredibly challenging for humans. Now let's take a look at that really quick. So microgravity causes changes in the circulatory system, altering blood pressure, the fluid volume. It atrophies muscles due to not being able to use them when standing. And it also de-densifies bones. Radiation, especially heavy ions, have the ability to cut DNA. So we need to come up with countermeasures for all of these things. So what tools can we develop to improve humans and ensure they're performing at their best? Well, taking a look at mental workload. Mental workload is a very strong indicator for human performance, and it's taking a look at how hard you are thinking. Right now, we quantify that with questionnaires such as the NASA TLX and the instantaneous self-assessment, as you'll see below. And this requires self-reflection on the part of the person being questioned and accuracy. This is really hard sometimes. Humans are susceptible to biases. And also, if they're performing a critical task, you don't necessarily want to interrupt them and be like, hey, how hard do you think you're thinking? Are you okay? So how can we think about thinking smarter? Now, if we were to have a device that was going to be quantifying mental workload, especially on orbit, it would need to be portable, very small form factor. It would need to be non-invasive, so the astronaut would be able to take it off and put it on again. It would be able to perform diagnosticity, that is to say, evaluating where the mental workload is coming from. Is it an auditory workload? Is it a visual workload? Is it processing? And we would also need to have it work in space. Some of the options that we have to quantify mental workload are MRI, so very high fidelity, but very large footprint, requires quite a bit of power, weight, volume. EEG is also very good, but it is susceptible to noises, especially in the environment of space. We have heart rate variability and pupil dilation. However, that doesn't really tell us how we are thinking and what portions of the brain are activated. So enter FNIRS. Again, FNIRS is functional near-infrared spectroscopy, and it is using infrared light that is sensitive to oxygenated and deoxygenated hemoglobin specifically. It's actually very similar to your sport watch, and so much like your sport watch, you have a source, and you have a detector for this IR light. And due to the BOLD principle, so the blood oxygen level dependent signal, your brain, when it is thinking, it allocates a region to perform the task, and as it is performing the task, the neuronal activity increases the oxygen usage and metabolism to that area. So if we can take a look at the oxygen usage of a particular portion of the brain, we can make inferences about how you are thinking. So as you think, that increases the oxygen metabolism of a region, and if you bounce infrared light against the particular location and measure the return, you can make inferences as you monitor these populations over time. If you add additional sources and detectors, you can monitor additional locations of your choosing. So again, there's two wavelengths, oxygenated and deoxygenated. This is a source, and you can see the two LEDs for each respective wavelength. You can tailor design however you want to monitor the brain or which portions of the brain you want to monitor with a 10-5, 10-10, or 20-20 EEG montage, and that looks something like this. So right here, we're taking a look at the frontal lobe of the brain. And underlying it, we can take a look to see that we are overlaying it with the Brodmann's areas responsible for information processing. So what do these observations look like over time? These are actually my observations. And as we can see the pulse as your brain shuttles oxygenated blood over and over via your heart. And what can we do with this information? Like, this is very cool to look at. But if we convert this to changes in optical density using the modified Beer-Lambert law, so the Beer-Lambert law is specifically tailored to human tissue, and perform a general linear model, removing a lot of the noise you would see, such as respiration, Mayer waves, and your heart rate, we can take a look to see how it changes over time. And as we can see the pulse in one's head. I tilt my head forward at this point, and you can see how the oxygen changes in the blood over time. So from this, we could take a look at how mental workload and which portion of the brain is performing the task. On the horizon, more research is needed to characterize mental workload, especially on orbit, because of the aforementioned slide talking about how your circulatory system changes because we are monitoring your blood and your blood volume changes. Additional characterization is needed to ensure that it is accurate on orbit. But also importantly, this is so applicable to anything on Earth that is interacting with a human. So if you want to evaluate if a human is utilizing a software and it's easy or hard, or driving, this technology and like quantifying mental workload would be particularly important. Cool. Any questions? Please reach out to the email address above. Thank you.